Hello and welcome to Mrs. Schaaf's classroom. Today we're going to be talking about thermochemistry. In particular, we're going to be looking at calculating enthalpy of a system and determining if our reaction is endothermic or exothermic. So we're going to be working through 4 or 5 problems, so let's get started. Okay, so let's get started on our problems. So here we have a reaction of butane with oxygen, so we have a combustion again reaction. The delta H, the heat of the reaction, is a negative 2,658 kilojoules. And the problem asks what mass. So that's what we're going to be looking at, is what mass. So we're looking at what mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat. And then once we finish that problem, there is a second, is what is the mass of carbon dioxide that is produced. So this kind of goes back to our limiting reagents that we did earlier. So let's just go ahead and look at the reaction. One is we always do have to make sure that it is balanced. And one of the things you might notice a little different than what we normally see is the 13 halves. So normally when we balanced reactions and so forth, we did go ahead and just double everything when we had the 13 halves. And you are welcome to do that if you don't want to work with the fraction. So what I mean by that is I could just go through and double everything, which would make this coefficient 2, this one 13, this one 8, and this one 10. So then you would not use the 13 halves. Or of course you could do 1, 13 halves, 4, and 5. And you could always change your 13 halves to 6.5 if you liked that better. So let's go ahead and get started. Let's see what we're doing. So we're starting off with the fact that we know our heat of a reaction that our butane is going to produce. And we want the mass of butane. So that's the one we're looking at here, mass of butane. So let's start our process. So what I would do is I would start with my given. So I would start with my 1.5 times 10 to the third kilojoules that I know I would like to produce. And I know that with butane, 1 mole of butane will produce a negative 2,658 kilojoules. And so my kilojoules are going to cancel, and now I have moles. And for moles, I need to go to our grams of butane, our mass. So 1 mole of butane would have a mass, and again you can calculate that or look it up, and what I looked up showed 58.12 grams. Okay, and again that's going to cancel, so be sure you check my calculations also. And that's all I needed, what mass of butane in grams is necessary to produce. So I started with what I was going to produce. I know my mole to kilojoules, 1 mole produces this much. Again, and then I need mass instead of moles. So let's go ahead and run through our calculations. Okay, and when I did my calculation of my 1.5 times 10 to the third times 58.12, I got 87,180. And then the negative 2,658 times 1 is, of course, is just that number. And then dividing it out, I got a negative 32.799, again, grams of butane. And then our significant digits, it looks like we're only going to have 2 in this problem. So that's going to make this go to actually to a negative 33 grams. And then we're done. Okay, so the next thing that we need is to do the second problem. So if that is true, then what is the mass of carbon dioxide produced? And again, we did this kind of stuff when we did limiting reagents and so forth, but basically I'm just going to do a mass to mass conversion. Okay, so I've got the negative, and I really don't even need the negative, sorry, on there because my mass is not going to be negative on there. And really this should have canceled out. I guess I again skipped something. Since I was producing this, I'm getting rid of it, negative, and then that should have been then positive all the way through. So my bad on that one. I wasn't even thinking as far as the signs go. Okay, so mass to mass, so I've got my 33 grams of my butane, and I know, again, my mole to mole ratio conversion is for, I need my butane and I need carbon dioxide. So butane being here, carbon dioxide being there. So I have 1 mole of the butane produces 4 moles of carbon dioxide. So there's my conversion, but I don't need moles, I need grams. So 1 mole of carbon dioxide is how many grams of carbon dioxide. And again, you can look that up or Google it real quick, whichever one the case may be. So I have it as 44.01 grams of carbon dioxide. Again, according to which periodic table you're using, your values there may be decimal values, may have more or less. Okay, so let's do our calculation. So we're just going to take our 33 times the 4 times the 44.01, and in which case I get 5809.32. And that's all over 1, so I guess that's all I need. That is grams of carbon dioxide, because everything else here is 1 and 1. Again, check for significant digits that we had. Earlier we said we did just have 2 is all I had. I had 2 to start off with here. So in which case this is going to round that to 58,000, or 100, I guess I should say, 5,800 grams of carbon dioxide. But again, I have told you guys to go to scientific notation, and that would be my... Okay, so here's my next one. No, the mass of hydrogen gas that's going to be required to produce this many kilojoules of heat. So again, it's still a mass or a heat to mass problem, so I guess it's not that much different than the last one we did. So let's just kind of, again, go ahead and get started. Oops, 226 kilojoules. And again, I know from my problem that the hydrogen requires that much heat. So 2 moles of hydrogen is a negative 483.5 kilojoules. Again, my kilojoules are going to cancel. I'm to the moles, and we know 1 mole of hydrogen gas is, what is that, 2.02, roughly, grams. And again, now we have the mass of hydrogen there, the minimum mass required, and we just need to run through some numbers. So let's go ahead and do that real quick. Okay, so I went ahead and finished that out. Now I did forget to put the negative on the 226 to start off with. So up here, I forgot to that again, just so that our negatives cancel out. Again, for the most part, if you want to leave off negative just because you know you're producing heat, in other words, our reaction is going to be negative because we're giving off or producing that heat. So anyway, it asks for grams of gas, and so I went ahead and divided it out. Please check my calculations. And 1.892 is where I took it, but then I've got 3 significant digits here, so my final answer would be 1.89. Let's try another one. Okay, so our next one here is what mass of, so again, I'm wanting mass this time of ethane, natural gas, must burn to emit, so it's going to give off, again, produce, that same word, 267 kilojoules of heat. So again, even though they don't put the negative there, it is a negative problem. So again, this is where I say you could, because of both of these are negative and we're working with mass, you really could just drop the negatives within problem. That would be acceptable, just so that you either add the negative or on this one, or drop it off of both of them, just so that you don't have a negative mass as I did in my first problem and realize that I needed to back up. So again, we're wanting the mass of the ethane, or yeah, methane, sorry, I don't remember what I call it, meth-eth-prop. So your methane, and here's our reaction. So we want the mass of that one. So I know that 1 mole produces an 800, whoops. Okay, so let's go ahead and get started then. So I am wanting, if this is the, and if you just think about, I have 207 kilojoules of heat. It requires 802 for 1 mole. That's definitely not a mole. So whatever mass I have is less than what 1 mole of that would be. Make sense of that. This is my amount that is produced in this reaction given 1 full mole of methane, but the amount that is produced is definitely less than that, so I should end up with less than a mole and less than the mass of a mole. So just thinking your way through it as to what your answer would be. So let's go ahead and get started. So I have 267 kilojoules that I would like to emit. I know that 1 mole is 802.3. Again, I'm dropping both of my negatives off. And so now I need that mass. So 1 mole is what in terms of mass? And again, you need to look that up and then run your calculations. Okay, so I looked up the mass. It was 16.04 grams. I multiplied across both my numerator and my denominator, divided it out, got 5.338, and significant digit-wise, because of the 267, I only have 3 digits. And again, going back to what I was saying earlier, 267, if you look at it, is less than half of what I wanted to produce, and the 5 is definitely half of that, so maybe even a third and a third of it. And so that answer does look correct as to what I predicted. Let's do one more. Okay, so this one is given again the formation of ammonia. N2 plus H2 gives us 2H3, ammonia, NH3. And so this time a little bit different because you see the energy here. So this is going to be, when you look at it, this reaction required to absorb energy and for it to happen. So absorption of energy is going to make this an endothermic reaction because it had to absorb energy. So this is asking how much heat energy is required to produce 29.2 grams of ammonia. So we want to know how much energy is required. So in this case, when I look at ammonia, I need 2 of those. I'm given grams. So let's, okay. And again, you can look at my numbers, pause if you need to. I got 39.4 kilojoules. And guys, if you just think about this, it takes 46 kilojoules, 2 moles of it. 2 moles is, if 1 mole is 10, let's just do a rough here. So 2 moles is 34 grams of ammonia, but I only had 29 grams to start with. So 29 grams that I needed to produce is less than the 34. Therefore, my energy is less than the 46, and it was. So again, think about whether your answer makes sense or not. Okay, so that is you 4 examples. If you notice, I probably have to go back and edit my video, so I'm going to have to cut some things out, but hopefully you can follow through. If you have any more questions, please don't hesitate to see me. This is Mrs. Shea signing out of Chemistry Classroom.